Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm really thrilled today to welcome Alan Ritter, who's visiting from all the way across the lake at the University of Washington, where he's a student with Ornetzioni. He'll be graduating this June, I think, with his PhD. Alan is well known to many of you from his 2 stints here as an intern, first in the machine learning group back in 2008, working with Sumit Basu, and then again in 2009 in the NLP group here with us. Alan's work with Sumit in 2008 won Best Student Paper Award. This was working on interactive machine learning techniques at IUI. Alan's work is focused, his thesis work is really focused at the intersection of natural language processing, social media, machine learning, and he's got some incredibly cool results to show you, I think, today. He has a Twitter-specific toolkit. He's worked a lot with big, raw, noisy data like Twitter, trying to extract signal from it, trying to extract structured information that can be used to enable new applications. And his toolkit has been used by many people. He's got it distributed on the web. I'll turn it over to Alan and let him talk about his exciting research agenda as he finishes up. Thanks, Alan.
All right. Yeah, thanks, Bill. Yeah, I'm really excited to be here, and please feel free to ask questions. Okay, so the internet's really changed the way that people communicate. And this has led to a huge amount of informal text that's available in electronic format. So this includes things like email, SMS messages, Twitter, and people are also writing informal text in professional environments, for example, physicians' notes and military field reports. Okay, so from my perspective, the really exciting thing about informal text as compared to formal text, say books or newspaper articles, is that the amount of it that's written each day is simply much larger. So just to make this a little bit more concrete, if we're to look specifically at Twitter, if we take all the tweets that are written in just a single day and print them into books, we'd have a pile of books that's as high as some of the tallest buildings in the world. And so clearly no person can read through all this text. And this is really why we need some sort of automatic text processing techniques to extract and aggregate and organize this information. And so there is actually a lot of important information that shows up first on Twitter. So one famous example of this is this Twitter user who happened to be in Abbottabad and live tweeted the raid that killed Osama bin Laden. And so, of course, this user really didn't know what was going on. But it turns out that also the first news that Osama bin Laden had been killed showed up on Twitter. So there was this guy who was a high-ranking official at the Pentagon at the time who leaked the information on Twitter before it showed up in the press. So people were talking about it on Twitter first. Okay, so of course there's been a ton of previous work on natural language processing and information extraction, which is focused on processing news articles. And I think this actually makes a lot of sense, because historically news has really been the best source of information on current events. And current events are a really good application area for information extraction. So if our goal is just to extract some historical information or kind of encyclopedic knowledge, it's really difficult to compete with these structured data sources like Wikipedia and Freebase. But news is also challenging for NLP applications for other reasons, in part because it's just already pretty well organized to begin with. It's not that hard to just sit down with the newspaper and get a good overall view of what's going on. So in the meantime, social media has become a really important competing source of information on current events. And so the status messages people are writing on these social networking websites have very different characteristics from traditional news articles. So they're short, they're easy for anyone to write, and they're instantly and widely distributed. So because of these reasons, they often contain fresher information on a wider variety of topics than news articles. But of course, this lowering of the barrier to publication is kind of a double-edged sword. So because these messages are so easy to write, we get a lot of irrelevant information, people talking about what they ate for breakfast, and there's also a lot of redundancy. So we get many people all talking about the same thing. And again, this leads to a situation of information overload and motivates why we need automatic text processing techniques to extract and aggregate information from this big, noisy text data set. OK, so when we look at applying NLP and information extraction techniques to Twitter, there's a number of challenges that come up. So for instance, there's a huge amount of lexical variation. So Twitter users are really creative in their use of spelling and abbreviations. And just to give an example of this, I ran a distributional word clustering algorithm on a large corpus of tweets. And so here you can see there's over 50 different ways that Twitter users can refer to the word tomorrow. OK, so secondly, tweets have really unreliable capitalization.
How do you know what to add tomorrow? Do you analyze the text syntax?
Yeah, that's a good question. So we're basically just looking at the context the words co-occur in. So they tend to occur in similar contexts. That's what the distributional clustering algorithm tells us. But I think these look pretty reasonable, yeah. Right, so in terms of capitalization, users will capitalize words just for emphasis, or they'll often leave the whole message lowercased. And this is pretty challenging for this named entity recognition task, which is a standard NLP task for information extraction. Traditionally for news articles, at least, named entity recognition relies heavily on capitalization, which isn't as reliable here. And then finally, tweets tend to have a unique grammar. So users will often drop personal pronouns, for example, assuming that the subject of the sentence refers to the speaker. And you just don't see these same kind of sentences in news articles. OK, so you might be wondering at this point, how do off-the-shelf NLP tools do when we apply them to Twitter? So I'm just going to walk through kind of a standard NLP pipeline here, going through this example and show where some errors come up. So first of all, the part-of-speech tagger thinks that this word yes is a proper noun, which is a pretty big mistake. And you can kind of see why. It's capitalized, and it's this funny spelling, so it's probably out of vocabulary. Then the chunker missegments its official Nintendo as a noun phrase, which is another big mistake. And the named entity recognizer missegments America as a location, whereas if you look carefully, you'll notice it should have really been North America. And so I'm not even highlighting all the mistakes here. But the point is that Twitter has this noisy and unique style, which these tools designed to work on grammatical text were just never meant to handle.
What kind of tagger do you produce this?
Oh, so this is a state-of-the-art off-the-shelf taggers. So these are from the UIUC group, actually. Yeah. So we also.
It's not trained using this data.
No. Yeah, it's trained on news data. Yeah. Mm-hmm. Right. So of course, yes. I mean, to deal with this, we've rebuilt an NLP pipeline, which is trained on in-domain Twitter data. And so, the main approach we're taking here is a supervised learning approach. So I basically just went and annotated a bunch of tweets with part-of-speech tags, shallow parser chunk tags, named entities, and events. We're also using some semi-supervised techniques, for example, using these unsupervised word clusters as features. And I think there's a lot of interesting work on unsupervised learning for syntax, but we're really trying to take a practical approach here and get something working on Twitter. So that's why we're taking this supervised approach. So I think there's actually a lot of room for interesting work in unsupervised learning for these more semantic level tasks. And I'm going to talk about these later in the talk. So we've done some work on named entity categorization, classifying the events, and also unsupervised relation extraction. OK, so here I'm showing the performance of our NLP tools, the shallow syntactic annotation tools, compared against off-the-shelf tools, which are tuned to work on newswire text. And you can see that in each case, we're doing much better than the off-the-shelf tools. We've made these tools available on GitHub, so you can go download them and use them if you're interested. And we've actually found that there's a relatively large number of people that are finding them useful. OK. So given that we have access to these tools which are tuned to work on this noisy in-domain Twitter data, a natural question is, what can we actually do with them? So to give one answer to that, I've built a system which is automatically extracting a calendar of popular events coming up in the near future. So to do that, we're continuously processing a stream of about 2 million tweets per day, running our NLP tools on them. and extracting, for example, named entities and events. In addition, we're also extracting and resolving temporal expressions. So for instance, if we see a phrase like next Friday, we can actually figure out the calendar day that's referring to. So then we can just count the number of times that each named entity co-occurs with a reference to each date, and use a statistical test to determine whether there's a strong association there and plot the most strongly associated events on a calendar. OK, and so I also want to highlight briefly here, there's a number of systems building issues that come up when we try to do this. So because we're processing so much data here, we found that just using a standard relational database just couldn't keep up with the number of inserts. Instead, we had to move to using this distributed NoSQL database. OK, so I'll go ahead and show a demo of this. And this is available online. I'd invite you to go check it out. So today is April 2nd. So looking ahead to Sunday, you can see there's a lot of people mentioning something about the FAA. We can click on that to drill down and get some more detail. And so here I'm just showing all the tweets that mention FAA in addition to April 7th. And you can see that they're basically shutting down 173 air traffic control towers this Sunday. And of course, this is due to the sequestration. So looking a bit further ahead, you can see that next week on Saturday the 13th, Mubarak, who is the former president of Egypt, has a retrial scheduled. And then on the 14th, Venezuela has new presidential elections. And so there's a lot of other stuff on here as well. I'd invite you to go and kind of check it out.
All category or only news part?
Yeah, it's from all the categories. So we do some language identification to filter out only the English tweets. But yeah, so this is kind of open domain. It's on kind of all different types of events and sources.
So what's that, the keywords about set?
Yeah, right. So this is these are these event words that we're extracting. So we've annotated some data to train an event phrase extractor. So this is kind of similar to the time bank corpus, if you're familiar with. So we're doing sort of a similar extraction task on Twitter.
How do you rank the top?
Yeah, so that's the statistical test, right? So we basically look at like how frequent is the entity and how frequent is the date, and then how often do they co-occur together, right? So if we just go directly by frequency, then like Justin Bieber would be the most frequent thing for every day, basically, right?
How did you filter out those information like what breakfast? What do you eat for breakfast? There probably more tweets like that.
Yeah, so that kind of comes out naturally from the statistical test. So there has to be like something that's happening really strongly associated with this day. So if people mention what they're eating for breakfast every day, you'll have to see it mentioned very frequently to kind of overcome the baseline, right? Yeah. OK. All right, so I think this just provides some motivation for why we want to do information extraction and natural language processing in Twitter. So we were actually pretty surprised to see that this works so well. So if you try to do something similar with newspaper articles, it's actually a pretty difficult task. So just to kind of explain why that is, for example, in this instance, to figure out when the bomb attack mentioned in the first sentence takes place, we have to recognize that the blast mentioned in the second sentence is referring to the same event, and also that the blast takes place on Saturday. And then to make things even more complicated, we have to further recognize that this other bomb attack, which is mentioned later in the article, is referring to a totally separate event which happened on a different date. So in order to kind of link together all the information in news articles, we have to solve these discourse-level processing tasks which link information together across sentences. And these are some of the more difficult and, I would say, unsolved problems in NLP. There's a lot of interesting research going on in this area, but we don't really know how to solve these problems in the same way we know how to take an individual sentence and process it. So in contrast, tweets tend to have really simple discourse structure. So users on Twitter sort of say things in really straightforward and compact ways. And to kind of understand why this is, if you imagine a user writing a message on Twitter, they typically assume that it's going to get mixed up in the feeds of all their followers, and so they don't assume any context that it's going to be understood in. In contrast, the sentence in a news article is really meant to be understood within the discourse context of the article. Okay, and so the point to take away here is that by working with these short, informal messages on Twitter, we're able to sidestep some of these complicated discourse issues. Okay, so given that we can do a pretty good job of extracting open domain events from Twitter, a natural question for us was whether we can categorize them into high-level types. For example, sports events, political events, product releases, and so on. And so this would have a number of benefits. Probably the most obvious thing here is it would allow users to browse more customized calendars which match their interests. So there's a number of challenges that come up when we look at categorizing events on Twitter. So the main thing is that there's just a huge number of different types of events that people can talk about. And in advance, we're really not even sure what the right set of event categories is. So furthermore, the set of important types might actually change over time as new topics become more or less important. Or if we want to focus in on a specific group of users, there might be a different set of categories which best describes the data. Okay, so to address these challenges, we're proposing an unsupervised approach to event type induction, which is based on topic models. And this is actually based on some work we've done on modeling selectional preferences with topic models. And so this approach has a number of advantages. It allows us to automatically discover an appropriate set of event types which match the data. We don't need to annotate any individual events in context. And we don't need to commit to a specific set of event types in advance like we'd have to do before annotating data. Okay, so how these generative probabilistic models work is we first make up a story about how our data was generated, which involves hidden variables and probabilities. And then given a fixed data set, we're going to apply Bayesian inference techniques to infer values for the hidden variables, which will then tell us the category of each event in context. So I'm just going to walk through a really high-level explanation of the generative story for our model here, just to kind of make it clear what's going on. So we'll start out by grouping together all of the tweets which mention the same event phrase. So in this case, all the tweets mention the word announce. Okay, and so then we're going to have a set of event types. So each type will have an associated probability distribution over named entities. So for example, for product releases, we might see entities like Microsoft, Samsung, and iPhone. And then similarly, we'll have a type for politics and sports. So then each event phrase will have a distribution over these types. For example, you can see that an announcement could be part of a product release or a political event or a sporting event. And then to generate the named entities in our data, we'll just repeatedly draw types from this distribution, and then generate the named entities in our data based on from the associated types. Okay, and so this just, oh, yeah.
I didn't understand what you meant by the event. So you just take the verb, if the verb matches?
Yeah, so right, so part of the NLP tools that I kind of glossed over a little bit was extracting phrases which refer to events, right? So we basically annotated data using the same guidelines as like the time bank corpus. And then so it could be like verbs or nouns can refer to events. You could have sort of like attack or attacked, right?
So the event, but are they pre-prescribed event types, or are you clustering to create the event types? Or?
Yeah, we're clustering to create the event types, right? Yeah. Okay, anyway, so this just kind of describes the generative story here. In practice, what we'll actually do is to apply Bayesian inference techniques, which will then give us reasonable values for the hidden variables, which will then tell us what the types are, and also tell us the type of each event in context. Okay, so we gathered about 65 million of these entity event date tuples, which are basically the same thing we're showing on the calendar. And for inference, we're using collapsed Gibbs sampling, which is actually a pretty standard approach to inference in these types of models. In practice, we actually use this parallelized approach to Gibbs sampling. So I should mention that Gibbs sampling is really an inherently sequential procedure. But there is some theory that explains that the parallelization can be understood as an approximation to the sequential sampling. And we actually found this to work really well in practice, and it lets us scale up to much larger data sets.
You have different chain? Or?
Yeah. You run a separate chain on each machine, and then at the end of each iteration, basically synchronize the counts.
So how do you decide what are the event types?
Yeah, that's a good question. So that's basically, right, so the runtime here is sort of like order the size of the corpus times the number of types. So this is kind of as many as we could do in a reasonable amount of time. Yeah, so of course there's work on like non-parametric models that try to find the right set of types. I think for these, if we're just trying to find event types, the number of types kind of doesn't matter that much. If you're looking at something like coreference resolution, then getting the right number of types is really important, and maybe the non-parametric approaches are more appropriate in that situation. But yeah.
Can you go back to this Bayesian network model? I want to see exactly which states correspond to what kind of auto-generated storage.
This part you mean? Yeah, right, totally. Yeah, so this is, I've kind of gave a little bit of a simplification there. So basically, right, so here we have for each type, it has a distribution over named entities, and then also a distribution over dates on which events of that type occur. And then the theta up there is the distribution over types for each event phrase, right? If that makes sense. So maybe I can use the laser pointer. It'll be a little easier to.
And the clustering that you did earlier on, part of generation, where does it go to here?
Yeah, so basically, right, so these hidden variables here, if we infer values for these will basically tell us the category of each event in context, right? And it'll also tell us, if we just can, basically in the inference, we do this collapsing. So we integrate out these parameters and then also these parameters. So all we're really doing is inferring values for these, which then you can kind of read off, what are the
observation that you have are the words in the tweet? N or D or something?
Yeah, so the observations are basically the event phrases, which so we're using a linear chain CRF to extract event phrases and then also to extract named entities. So this is kind of on top of that, right?
N is named entity and D is, there's one D and N. But
right. Yeah, so these are the dates.
Entity you extracted.
Yeah, so this, right, so basically, right, so we also extract and resolve these temporal expressions. So I'm skipping this in this kind of higher level story. But so basically, each type of event has a distribution over dates on which events of that type happen to. So this kind of helps to group together tweets which are referring to the same event, which of course have the same type.
Okay, so now with the observation really is just not the word, it's the extracting information from the word.
Exactly.
Okay.
Yeah, totally. Mm-hmm.
So what's the resolution of the date? So is it like day or months or week?
Yeah, so we just went with just days, right? So you could imagine someone says like, oh, at 8 o'clock on Thursday, I'm going to do this. But for the Twitter data, it seems like most events that people are talking about they just give you the specific date on which it happened.
So you mean for each event type, you have a distribution over the 365 days?
Yeah, or just more than 365. So I mean, it could be at any time. Yeah. So this is a little bit counterintuitive, and we tried doing it with and without this. But basically, the effect that ends up having is grouping together events that happen on the same day. So maybe on this day, there's like a really big, sports event that's happening, and so.
Yeah. So as you showed earlier on, all this, tagger, etc., information extraction component are subject to errors because of noise in
Yes.
of this.
Yes.
So ideal solution would be that parameters on those models,
Yeah.
is supposed to be part of that model, so you do end-to-end learning to
Yes.
correct those errors.
Totally.
Do that now? You separate them.
Yeah, I'm doing it separately. I think it would be interesting for future work to look at a joint model here. So I think the advantage of this approach is that the inference remains pretty simple, and so because we're working with a lot of data, it lets us scale up to a lot of data. I think that it's interesting for future work to try and do an end-to-end joint approach. Yeah.
I just want to make sure I understand. So the 100 event types have been clustered ahead of time before you've done this inference, right? So you do that, and then you create the model, and you infer the distributions of entities and whatever over the event types, or is the clustering happening during the?
Yeah, the clustering is happening during the inference. Yeah.
The byproduct of the.
Yes, that's correct. Yeah. So basically, we just find for each named entity sort of like what event type does it have, and then at the end we can kind of read off the clusters from that, right?
But you are limiting it to 100. So there's somewhere in the inference and learning process where it's reclustering sort of on every. It's doing like an iterative reclustering thing.
Yeah. Right. So basically, the Gibbs sampling procedure, how it works is we basically go through all the data and then sample a new. For each hidden variable, we just sample it. As we're going through the data, resample a new value for it, and then yeah, do that through the whole data a couple times, basically, or 1,000 times. Yeah. Okay. All right. Okay. So anyway, so these are some of the event types that are automatically inferred by our model. And I think these look pretty good. So for example, we have like a sports type here where we see event words like tailgate, scrimmage, tailgating, homecoming, and regular season, and then entities like ESPN, NCAA, Tigers, and Eagles. Oh, and I should mention, by the way, that these labels are just kind of my interpretation of what the events are. These aren't automatically generated. Then we also get a nice TV event here where we see event words like new season, season finale, new episode. And then we're seeing some TV shows like Jersey Shore, True Blood, and Glee, and also TV networks like HBO. Okay, and so we also did an evaluation where we looked at the ability of our model to actually categorize events in context. And so I manually annotated some data with the event types which were automatically discovered by our model. And so here we're comparing against a supervised classifier as a baseline. And basically the point here is that by using large amounts of unlabeled data, we're able to do better than the supervised baseline.
Supervised, because these were the inferred categories.
Yes.
So you're trying to make your own interpretation and.
Yeah. So basically, we run inference in the model. It'll give us, it'll automatically infer some categories, right? And then basically, I'll use those same categories that the model kind of automatically inferred to annotate some separate data, if that makes sense.
But to some degree, then this is a test of how well you understood the underlying categories that were inferred.
Yeah, that's true. It's a little bit. I mean, I'll agree that it's a little bit. It's a little bit weird. I mean, I see your point, but I mean, I think there's some advantage to like just automatically finding the right set of categories for the data. Yeah, totally. And I mean, I think right. So that's right. So I mean, I think it's kind of it is a little bit odd. I'll say to say like, oh, we have this unsupervised model that's doing better. And I think part of the reason why people have found that supervised models tend to do better is because that what the unsupervised model is finding doesn't really match up with your idea of. So this is kind of like I'm going to like let the unsupervised model find something, and then I'll like use that to annotate the data with. Yeah, that's basically what's going on here. Yeah. Okay. Right. So this unsupervised approach to information extraction has a number of advantages. So it lets us scale up to large unlabeled data sets. We don't need to specify the right event categories in advance. But I think there's an interesting question here, which is what to do in the situation where we have access to large amounts of structured data, for example, from Freebase or Wikipedia. And this is actually the case in this next task that I'm going to talk about, which is named entity categorization. So here it's pretty easy to get large lists of named entities and their types from these structured data sources. Okay, so there's a number of challenges that come up in named entity categorization in Twitter. So there's a huge number of different types of named entities that people are talking about. So they're talking about bands, movies, products, and so on. And many of these are going to be relatively infrequent in the data. So even in a really large manually annotated data set, there's going to be few examples of these infrequent categories. So because of this, I think we can't simply rely alone on supervised learning alone here. Okay, so the second thing that's challenging is that tweets are very terse often. So for example, in this instance, it's really hard to know what type of entity KKTNY is referring to without some additional background information. Okay. So to address these challenges, we're proposing a weakly supervised approach to named entity categorization, which uses large lists of named entities and their types gathered from Freebase as a distant source of supervision. Okay, so of course we can't simply just look up a named entity to figure out its type and context. So for instance, if we look up China in Freebase, we see that it could refer to either a country, there's also a band called China, there's a number of different people whose name happens to be China. So we need some way to disambiguate between these different possibilities. Okay, so to do that, we're proposing a new approach to distant supervision, which is based on constrained topic models. And so like I mentioned, or like I kind of alluded to in the previous slide, just applying distant supervision directly to this task doesn't work because the training data is just too ambiguous. So instead, we're proposing a latent variable model for named entity categorization, which uses the freebase dictionaries as constraints in the model. OK, and I'll try and make this a little bit more clear on the next slide. So again, here I'm kind of showing the high-level version of the generative story for our data. So in this case, we're grouping together all the tweets which mention the same named entity. And then each entity type has a distribution over context words which co-occur with mentions of that entity in context. OK, so so the key difference here is that these type distributions for each entity are constrained based on the freebase dictionaries. So for instance, if we look up JFK in freebase, we might see that it could refer to either a person or an airport, and then we'll constrain its possible distribution over types based on these possibilities. OK, and then like before, we'll repeatedly draw types from this distribution, and then to generate the context words in our data, we'll pick them from the associated entity type distributions. OK, and so again, this is just a description of the generative story. In practice, we apply Bayesian inference techniques to infer values for the hidden variables, which then tell us the category of each named entity in context.
So what's your context?
So basically, so we just use the previous and following 3 words, and then we also use the words in the entity as well, right? OK, so here I'm showing some example type lists which are automatically generated by this model. And this is just for 3 out of the 10 types that we're working with. And these, I should mention, these are also some of the more difficult types. So the easy things are like person and location. But I think these actually look pretty good. So for example, so this is basically these are the top 20 entities which weren't found in any of the freebase dictionaries. So these are like words that our model was able to categorize automatically. So for products, we're seeing things like Nintendo DS Lite, Apple iPod. There's some segmentation errors in here as well, but iPod Nano and so on. But I think what's really cool here is that we're able to correctly categorize some of these Twitter-specific abbreviations, which you just wouldn't expect to find in freebase.
So what's that?
Oh yeah, these are TV shows. I don't know. I hear about all this stuff. I don't actually watch these shows though. Yeah, I don't know. That's part of the fun of working with Twitter data. OK, anyway, so we also looked at how well our model can actually categorize named entities in context. So I annotated a large corpus of tweets with named entities and their types. And here I'm showing our performance compared against a bunch of baselines, including a supervised baseline, which actually does really well on the more frequent types like person and location, but does poorly on these infrequent types where there's few examples in the training data. We also compared against the co-training approach to weakly supervised named entity categorization proposed by Collins and Singer. And you can see that we're actually doing quite a bit better here. OK, so why is it that LDA is winning in this case? So I think there's a couple of reasons for this. So the first is that it's able to share information about an entity's type across mentions in a really nice way. So basically, we can figure out the right type of the entity in these highly ambiguous cases by looking at the same entity in other contexts. So the other thing is that because we're using these freebase dictionaries as constraints in the model, we're just better able to take advantage of this highly ambiguous training data. So we don't have to just rely on these unambiguous cases to learn how to categorize the entities. OK. Oh, yeah.
On the supervised baseline, what did you do for that?
Yeah, so I annotated about 2,400 tweets with named entities and their types. And we basically just used like a maximum entropy classifier.
Is it using the same context, or the 3 words before, 3 words after?
Yeah, the same
Did it use
features.
freebase then?
Did it use freebase?
Yeah, did you take advantage of the context of anything that appeared in freebase?
Yeah, no, I think it didn't look at freebase at all. So we did also have a freebase baseline where we basically look up the entity in freebase, and if it's unambiguous, make that prediction. And this actually has really high precision, but the recall is pretty low. Yeah. OK. All right. So yeah, so I just talked about this new approach to distance supervision based on topic models, constrained topic models, which is appropriate for the situation where you have highly ambiguous training data, like this named entity categorization task. So there was a natural question that came up while we were working on this, which is what happens when there's missing information in either the text or the database? And so the answer is this leads to errors in the training data. And this is a really general problem that affects distance supervision, both for this weakly supervised named entity recognition task I talked about, and also for the more common application of distance supervision, which is extracting binary relations. OK, so for the sake of comparison to previous work, so here we're looking at the case of binary relations. And so it turns out that most of the work in relation extraction uses a huge number of features which are highly correlated and overlapping. And so these generative models that I've been talking about are kind of not a very good fit for this data because they make really strong independence assumptions. So instead, at this point in the talk, I'm going to move on and talk about conditionally trained models. OK, so this is kind of like what the setup looks like for extracting binary relations using distance supervision. So we'll start out by having a relation, in this case the born-in relation. And then Freebase is going to give us a large list of people in the locations where they're born. OK, so basically for each pair of entities here, we can go and search through a large text corpus and find all the sentences which mention the entity pair, so Barack Obama and Honolulu in this case. And then we can basically just treat these as positive examples of the born-in relation and extract features from these sentences and train a supervised classifier. OK, so this is great, but the problem is that what happens if there's some information missing from Freebase? So in this case, all of these sentences function as now a negative training example for the born-in relation, which I think you can see is a problem. And this is actually a pretty common scenario. So there's actually a lot of information missing from these databases. And that's kind of the whole reason why we want to extract information from text in the first place. OK, so before I get into the solution of how we're going to deal with this, I'd like to just walk through a model for distance supervision in the context of extracting binary relations. So we'll start out with a pair of entities, Barack Obama and Honolulu in this case. And then we're going to get to observe all of the sentences which mention this entity pair. OK, so now we're going to have a classifier, which is going to predict for each sentence what relation it mentions between these pair of entities. So unlike the standard supervised learning setup, we're not going to actually get to observe these variables during training. Instead, we only get to see these aggregate level variables, which tell us which relations hold between Barack Obama and Honolulu in aggregate. So the question here is, how do we relate these aggregate level variables that we get to observe with the hidden sentence level relation mention variables? And so one answer to this question is a simple deterministic OR function. And so basically what this is saying is, if any of the sentences mention that Barack Obama was born in Honolulu, then this fact is true. If none of the sentences mentions it, then it's false. OK, and so we can then tune the parameters of this model by just maximizing the conditional likelihood of the observed facts in Freebase conditioned on the observed sentences in the data. OK, so for learning here, we're taking an approach based on the structured perceptron, which is an iterative gradient-based update to the weights. In addition, we're taking an online approach to learning, which just means we update the parameters after seeing each pair of entities, rather than going through all the data and doing batch updates. OK, so this is what the gradient looks like. It's just the difference between these two expectations over the features. And so in practice, these expectations are too difficult to compute. So instead, we approximate them with maximizations. So basically, what's going on here is we have two inference problems. One where we want to find the best assignment to the sentence level hidden variables conditioned on the observed sentences and facts in Freebase. And in the other case, we just want to find the best assignment to the sentence level hidden variables given the current parameters, but ignoring Freebase. OK, and so the unconstrained inference problem is totally trivial. But the constrained problem is a little bit more complicated but it turns out that it reduces to this weighted edge cover problem, which we can solve exactly in polynomial time. So this works out pretty nicely. OK, so there's two assumptions that are being made here. So if a fact isn't in Freebase, we can't extract it from any of the sentences. Whereas if a fact is in Freebase, we have to extract it from at least one sentence. And so these assumptions are good because they help to drive the learning. But in the case of missing information in either the text or the database, they lead to errors in the training data. OK, so how might we modify this model to more gracefully handle the situation of missing data? So what we're proposing to do here is to take these aggregate level hidden variables and split them into two parts. One which represents whether a fact is mentioned in the text, and the other which represents whether it's mentioned in the database. And so then these factors between the two variables are going to encourage but not require that they agree with each other. So now you can see that the facts in Freebase are acting like soft constraints, whereas before they're like hard constraints. So for example, now it's possible to extract a fact that's not in Freebase if the local classifier is highly confident. But of course, we're going to have to pay some penalty for doing that. OK, so the learning is pretty similar to before. So the only difference here is that we're now maximizing over these additional aggregate level hidden variables that we've introduced. And it turns out this doesn't make any difference for the unconstrained inference problem. But the constrained inference problem gets a little bit more difficult. So it no longer reduces to this weighted edge cover problem in a nice way like we had before. OK, so of course, the question here is, how are we going to solve this inference problem? So again, the goal is to find the best assignment to the sentence level hidden variables conditioned on the observed sentences and facts in Freebase. And like I mentioned, this is just kind of an optimization problem with soft constraints. OK, so basically what we found here, so we looked at a couple different approaches. So we looked at some exact inference approaches like A*, which are time and memory intensive, and so don't really scale up to these really large data sets we're working with. But we found that a local search almost always finds an optimal solution, so long as we use a carefully chosen set of search operators that are designed so that it doesn't get stuck in a local maxima. And so to verify that we're finding optimal solutions, we can compare against the solution found using A*. And we found that in over 100,000 problems from our actual data, we only missed an optimal solution 3 times using this approach. And so this is nice because it's fast and memory efficient. And it almost always finds an optimal solution. OK, so of course, the real question is, how does this affect the performance in terms of precision and recall? And so the answer is it actually makes a big difference. So here I'm showing precision and recall curves on the sentence level extraction task, comparing against human annotations from the data. And so the red curve here is the system which is using hard constraints. By simply relaxing those as soft constraints and setting 2 handset parameters in the model, we're able to get the black curve, which is actually a huge improvement. And then by incorporating some additional information in the form of a missing data model, we're able to do even better, which is the green curve here. And so I think people realize that these distant supervision models are making some bad assumptions about the data. I mean, all models have to make assumptions, right? But I don't think they realize there's this much room for improvement by better modeling the data in this distant supervision problem. OK, so I'd like to just pause for a minute here and summarize what I've talked about so far. So I presented an analysis of the challenges in applying information extraction to noisy text. I talked about our NLP tools we've adapted to Twitter, and these are available online. You're welcome to go and use them. I showed this demonstration of a system I've built, which is automatically extracting a calendar of popular events coming up in the near future. And then I presented 3 different probabilistic models for unsupervised information extraction, one which is doing unsupervised event categorization. I also talked about this new model for distant supervision using topic models, which is appropriate for the case of highly ambiguous training data. And then I also showed this recent work we've been doing on modeling missing data in distant supervision. Right, so I'd like to spend just a little bit of time mentioning some other work that I've been doing during my PhD. So I've been collaborating with some folks here at Microsoft Research, Bill and Colin, who's now at NRC, on modeling conversations in social media. So in addition to talking about popular events, users of these social networking websites are having conversations on a really large scale. And I think this opens up all kinds of new opportunities for data-driven conversation modeling. So for example, we've done some work on unsupervised modeling of dialogue acts and also automatically generating responses to Twitter status messages. And so I'll elaborate just a little bit on this second point. So the approach we're taking here is based on statistical machine translation. So in machine translation, the task is given some foreign text, we want to translate it into English. And in order to learn a model to do this, we have access to large parallel corpora of paired foreign and English sentences. So I think in some sense, this conversational task is actually kind of similar. So given an arbitrary user utterance, we want to generate an appropriate response to this. And to learn a model to do this, we have access to millions of naturally occurring conversations from Twitter. OK, and so at a high level, how phrase-based translation works is, given an input sentence, we first segment it into phrases, and then we translate each phrase in the input into a phrase in the response. And so this is a little bit different than the machine translation case. But so there's potentially some reordering here. And to find a good translation, we want both good translations at the phrase level and then also a high score according to a language model.
Somehow you require some certain kind of understanding in order to generate the response, right? Not like translation, which is literal.
Yeah, no, that's a good point. Yeah, so conversation and translation are two very different problems. Yeah, right. So it's right. So we can't have kind of very deep intellectual conversations. Basically, we're learning these kind of high-frequency response patterns. Like, if I see airport in the status message, maybe say safe flight, or like I translates as you, or like dinner translates as young. So these aren't very like deep kinds of conversations. But yeah. But right. So we have a demo of this available online. You can go play around with. So for example, I'm feeling sick translates as feel better soon, and this is like n best output, so you can see the other things. Yeah. Right, so I think, right, so this is kind of cute and all, but I think there are actually some interesting applications here. So one might be, conversationally aware predictive text input or speech recognition. So assuming that a user just, or assuming that your friend just sent you a text message, and you're typing a response to it using some noisy input mechanism, I think we can actually do a better job of predicting what you're trying to type by taking the message that you just received into account. So for instance, if your friend texted you saying, I'm feeling sick, we should be able to do a pretty good job of predicting how you might respond to that without even seeing any input from the user.
Is that just template matching? Get something is a method.
Yeah, that's a good question. Right, so I mean, right, so the hope here is that by combining information, actually generating a customized response, we can do better than or handle sort of a wider range of different things. I mean, I haven't done this experiment, right? So it's hard to say. I mean, template matching is probably a pretty strong baseline for this, for sure. Yeah.
So here the idea is that you learn this model, and that can serve as a language model to interpret those noisy light speech.
Exactly. Yeah. So you could probably get like the sort of translation lattice out of this or something, and combine that with the lattice from speech recognition or something. Yeah. Okay. So then I've also been doing some work recently in collaboration with folks at New York University, and actually also with Bill. So, but on paraphrasing between different language styles. So, for instance, we've been looking at paraphrasing Shakespeare's plays into modern English, and also, modern English into kind of a Shakespearean style. So the approach we're taking here is we've basically found, we've scraped a bunch of modern translations of Shakespeare's plays off the web, which we can then use as parallel text to build translation models. And so, like, for example, one thing we can do is paraphrase lines from modern movies into Shakespearean style. So for example, if you will not be turned, you will be destroyed gets translated as if you'll not be turned, you'll be undone. And Father, please help me is translated as Father, I pray you help me. And so there's a demo of this online as well. And again, these are kind of some fun examples. But I think there are actual applications here as well. So one thing would be educational applications. So it turns out there's only modern translations for 17 out of the 38 plays that Shakespeare wrote. So by translating these other plays into modern English, maybe we can actually make them more available to students. And of course, there's a ton of other authors from the same time period as well. I think looking at paraphrasing between language style and other domains is also interesting. So for instance, paraphrasing technical documents into more easily understandable English, or paraphrasing between noisy informal text on Twitter and more formal text. OK, so for future work, one thing I'm interested in looking at is extracting richer semantic representations of events from microblogs. I think people have spent a lot of time working on information extraction in news articles, but there's still a lot. I think there's still a lot of opportunity to sort of do a better job of extracting events from Twitter. So one problem here is sort of solving this event reference resolution problem, which is to group together all of the tweets which are referring to the same event. So we haven't really solved this yet. So I think the representation that we're currently extracting is nice because it's open domain, but I think there's sort of more opportunity here to extract a richer representation. And so also related to that is this problem of schema discovery, which is given these automatically discovered event categories, can we automatically extract schemas for them? So for example, for a concert, we might expect to see like a music artist that's performing at the concert, also the venue and the city where it's taking place. And then ideally, we'd be able to automatically extract and fill out these templates. And if we can do this unsupervised, then I think we can do it in an open domain way, which isn't restricted to a specific type of an event. OK, so a little bit more of a longer-term agenda for future work here. I'd like to look at scaling up grounded language acquisition to more realistic and open world domains. So I think we're in a really exciting position right now. So we have access to all kinds of real-time text in different languages. And in addition, we have all kinds of real-time sensor data. So for example, real-time data about the weather, traffic, seismographic data. And so I think there's an interesting question here of whether we can link events that people are talking about in text with events that are showing up in sensor data, and they're kind of temporally correlated with each other to give us some kind of signal there. OK, so one possible approach to this would be to extend some of the latent variable models that I've been talking about to incorporate both real-time text and sensor data. And maybe by doing this, we can ground the meaning of these distributional semantic representations that we've been learning in real-world sensor data at scale. OK, so I'd like to wrap up and just thank my collaborators. And thanks for coming to my talk. Yeah.
So in your Twitter work, so you use some other tools like password taker, chunker, and menu taker. So I want to know. So this is a pipeline, right? So they definitely have error propagations. But the problem is that one good thing about Twitter is that they have a lot of duplication on the tweet. So basically, how important it is to have to improve your button pipeline, basically password taker. And taker and chunker, or they are already good enough because they are already a lot of duplications, so you see a lot of mistakes.
Yeah, no, that's some good points you're making there. Right, so I think so in the calendar at least we are kind of exploiting a little bit this effect of redundancy. So if we see lots of people saying the same thing in different ways, that helps to improve the precision rate. So definitely I think there's room for improving the performance at part-of-speech tagging and named entity recognition. So one thing is just annotating more data. Like you're saying, some kind of joint model that looks across different tweets, right, is also really interesting. I think, you guys have been doing some work in this direction too, which I think is great. I guess my feeling is that probably the performance on these shallow syntactic annotation tasks like part-of-speech tagging and named entity recognition is sort of always going to be lower on Twitter than what we see in news articles, just because it's so diverse and noisy, right? So it's kind of more challenging from that aspect. But I think once we get past these noisy text issues, there's actually other things that become easier, right? Because it has this really simple discourse structure, like I mentioned. So it's kind of just this interesting domain with different characteristics than what people have mostly focused on,
About conversations, it looked like you were focusing on a sort of a stimulus-response pair. Conversations can go on sort of longer. Did you look at to do a sort of modeling of the sequence?
Yeah, so we did, in a little bit different of a context, though. So we also had some work on unsupervised induction of dialogue acts. So these would be things like, trying to classify each post as like, is it a question or an answer or a status post and things like that. So yeah, so there we're looking at the sequence and kind of longer conversations. Yeah, for the response generation task, we just picked like the first message in a conversation and then the response to that, just because that kind of constrains the problem a little bit, right? But yeah, doing that in the context of longer conversations, I think, is interesting, but we haven't looked at that yet. Yeah. Yeah.
To hear a bit about establishing your baseline, use the eating breakfast example.
Mm-hmm.
How do you set a baseline across these high frequency and low frequency entities?
Yeah, so we basically just count in our corpus, like for each entity, how many times has it been mentioned, as long as we have data for it, basically, right? So we basically count the number of times each entity is mentioned and the number of times each date is mentioned. And then we can look at the number of tweets that mention both of them and then just apply a standard statistical test like, chi-square. We use like a g-test. I mean, ideally what you do is Fisher's exact test, but with the amount of data we're working with, there's some like floating point overflow, I guess, basically that happens. But
Find you have to really set that baseline since there's emerging trends and so on?
No, that's a good question. Yeah, so we haven't really, I've just kept the same, I haven't reset it, but you probably could, it might actually be worth doing. I haven't really looked into that though. Good question.
So have you looked at what kind of errors that you have seen in AER, the pre-processing part? How do these errors affect your final output?
Oh, for the calendar, you mean?
Okay.
Yeah. So there's, there's a lot of segmentation errors, to be totally honest. So like movie names specifically are really hard because they're often sort of short phrases, right? So often you'll see, gosh, I'm having a hard time. Like if you have sort of Dumb and Dumber or something as a movie title, right? You might just get like Dumb as an entity or something, right? Instead of, they're really hard to distinguish.
To what extent do these errors affect the final calendar output?
Yeah, so basically in that case, for example, you would see just like, just the name that you're displaying would be incorrect. But still, you can kind of click on it and drill down and kind of see what happened. Yeah, I should, the calendar application, I think there's a lot of, I could have spent a lot more time engineering this and making it better. It's just kind of there certainly are some errors there for sure. Yeah.
So Twitter's a domain where people do some amount of manual tagging with hashtags and things like that.
Right.
And on the one hand, you could treat those just as another word, which happens to collapse across a lot of things, but maybe you want to treat them specially because there's some user intent going into depicting the same tag, and I'm wondering what your thoughts are.
Yeah, no, that's a great question. So I've just treated them just like another word so far, but I think there is definitely something to get out of them for sure. Some of them are, right, so in some cases they're really useful and they sort of, really give you an anchor on the event. In some cases you see things like #I like bacon or something like that, right? But, so I don't know, I think there's definitely something interesting to be done with the hashtags. I haven't really figured out what it is yet though. I've seen some interesting work on trying to segment them into words and things like that, right? Yeah, definitely like for conferences and things, it'll sort of like give you a nice focused group of all the tweets on this specific event. I think in some sense, they're almost kind of more useful for people just to,
So that might be, because sometimes you're trying to extract like a human readable label for a group, for instance.
Yeah.
So distribution amongst hashtags.
Totally.
Even if they're not perfect coverage, might be helpful to people because they're kind of engineered by people.
Right.
Or other ways in which they might.
Yeah. Or even if you just take all the hashtags that are taught, I tell you I want to know about this particular hashtag, and then just get all the tweets that mention that, and then, one interesting question is sort of how can you summarize all the information that people are talking about there in a short, easily readable way, kind of,
Or they could be used as supervised labels to kind of like, from which it's see.
Right, to find other tweets talking about the same event that aren't with the hashtag. Yeah, no, it's a good point.